Hello, everyone. It's really a pleasure to welcome you all to the Paul D. Allen School of Computer Science and Engineering at the University of Washington. It's our colloquium, and it's great to host Divya today. So Divya Mahajan is a senior researcher in the Cloud Accelerated Systems Technology Group at Microsoft. So she's been doing a lot of research in the intersection of and doing work that goes into production too, right? So work in the intersection of computer architecture, machine learning, and systems, and with some recent focus on massive scale distributed deep learning. She did her PhD at Georgia Tech, and her advisor is one of our dear alums, Hadi Esmailzadeh. And so it's always great to see all the awesome stuff to our alums, the awesome people that our alums help educate. So anyway, so she got many awards, published in all the key computer architecture conferences, also in very prestigious machine learning conferences as well. And it's really great to consider her for faculty position here. So Divya, please go ahead, and as I'll relay questions to you as we go. Okay.
Sounds good. Thank you so much, Lou. Thank you so much, Louise, for the great introduction. I'm Divya Mahajan. I'm a senior researcher at Microsoft. Today, I'll talk about my research in creating domain-specialized accelerators and systems for a very important class of applications, artificial intelligence and machine learning. The goal of these solutions is to strike a balance between generality and specialization for these compute and data-intensive applications. As we all know, machine learning is becoming more and more ingrained in our everyday life. Netflix uses collaborative filtering for movie recommendation, convolutional neural networks enable object detection and classification, translation models for Google Translate, and neural recommender models are used by Facebook to provide personalized ads. So at the same time that these models are becoming so ubiquitous, their scale is also growing significantly. One of the largest models today, GPT-3 by OpenAI, has 175 billion parameters. And to put this into context, what such a large model can do, the OpenAI's Codex model, which they have co-piloted with GitHub, aims to do automatic code generation, write English articles, do math Olympiad questions. So this growth that we have seen in the recent years of these large-scale models is also in part fueled by the unprecedented data growth that we have seen in the last decade. On this slide here, in the graph, on the x-axis, we see the timeline. On the y-axis, we see growth normalized to the year 2008. It is expected that the data will continue to grow at an exponential rate. However, the performance growth of general purpose compute platforms, especially CPUs, cannot meet the compute intensity of these emerging applications that process this data. So we have this gap. Specialization and domain-specific acceleration is a means where we create hardware designs which are tailored to the properties, the mathematical properties and the data flow properties of a particular application, and aim to meet the compute demands of these large AI and ML models. These specialized architectures are more performant and energy efficient. However, if we think about this space of specialization and generality, it's essentially a spectrum where we have various platforms, and each platform trades one for the other. On the one end, we have CPUs, extremely general purpose. Then we have GPUs. They are also fixed architecture, but more adept at doing coarse-grained and uniform parallelism. Then we have FPGAs and ASICs, which even allow us to explore the architectural space and create hardware designs tailored to a particular application or a domain. However, if we think about challenges, various challenges to use these particular platforms, GPUs, for instance, they are very high compute throughput, but they are power hungry and they are more adept at doing certain form of parallelism. They also face system level bottlenecks when deployed at scale. For FPGAs and ASICs, even though they allow us to explore the architectural space and create hardwares tailored to a particular domain, they have a high barrier to custom hardware. So why do we see this barrier to custom hardware? The reason for that is creating domain-specific accelerators is difficult and very expensive to design and use. The reason for that is it requires expertise both in hardware design and the application domain. often the accelerators that we have limited compute and memory resources. So how to deploy a particular application onto those limited resources incurs a long design and verification cycle. And all of these reasons make these domain-specific accelerators hard to leverage for high-level programmers. Also, if we think about the traditional way in which we have deployed these hardware accelerators, they have always been an ad hoc addition to the general purpose stack. Although they aim to bridge the compute gap, in the traditional way, we have always thought of accelerating one compute-intensive kernel of an application. So for instance, whenever we want to create an accelerator design, we used to look at an application, profile it, determine which is the most compute-intensive kernel, and create the accelerator which executes this kernel in a very efficient manner. However, the CPU runs the remainder of the application. Now, in this scenario, the focus of the accelerator is only on that particular kernel. And this means the accelerator cannot cater to the volatility of the application space. So if the profiling information changes or there's some change in the compute operations, we might have to change the accelerator design itself. Also, if we think about it, the accelerator is completely unaware of the end-to-end application. Is it running training or is it inference? And also it is unaware of the entire system in which it is deployed. Is a single accelerator performing execution or is it multiple accelerators? So overall, if we think about this problem of creating domain specialized architectures and systems, we face various challenges when we want to use each of the platforms, GPUs, FPGAs, ASICs. But the bigger picture here is that we want to continue the algorithmic innovation in this space and the data revolution that we are seeing. And for that, we have to take a very principled and deliberate approach in providing the infrastructure, both architectures and systems, architectures due to the current trends in the silicon technology, and systems because of the scale of the problem that we are seeing. By exploring the architecture, we can create more energy efficient solutions which are tailored for a wide class of, for instance, machine learning models and can mitigate the inefficiencies that we might see in fixed architectures. Systems, because creating just an accelerator is not sufficient. We need to think about the larger data processing pipeline, how data is stored, managed, retrieved, and if it requires any pre-processing before it needs to be sent to the accelerator. So kind of co-optimizing this larger data processing pipeline. In this space, we need to innovate across the system stack. The first challenge that I tackle in this space is the specialization gap. How do we reduce barrier to custom hardware? In this vein of work, I look at what are the new hardware software abstractions that we can create and move away from the canonical instruction set architecture and think about domain specialized computational stacks. The goal of this work is to allow high-level programmers to be easily able to leverage these domain-specific accelerators. And the goal with this work would be that these accelerators can cater to the compute intensity of the applications. The next challenge that I tackle in this space is looking at a larger data processing pipeline. All of these AI and ML models consume a lot of training data, and this data can be stored in complex data structures such as database management systems. So how do we integrate our domain-specific solutions within relational databases? Finally, in the context of memory and I/O, as the scale of the problem is growing in terms of the amount of data it is consuming and the size of the model, memory and I/O is becoming the bottleneck. So how do we dive into the properties of the model and the statistical properties of the training data to efficiently distribute the workload and do end-to-end efficient execution, either of training or inference? Today, in my talk, I'll talk about these three systems. The Tabla work, it was the first and pioneering work to create a full compute stack solution for a wide class of machine learning algorithms. It was a central part of my thesis, and it also led us to use the same insights and develop full computational stacks for a wider class of AI and ML models such as deep learning, robotics, and we even used the insights to create solutions for multi-accelerator executions. Then I'll very briefly touch upon Dana, which aims to integrate these full compute stack solutions within relational row-based relational database management systems. And finally, I'll talk about the most recent work, FAY, which looks at the statistical properties of the training data to efficiently place recommender model across CPU and GPU devices. Let's first dive into Tabla. This was, as I was mentioning, this was the first work to create a full stack solution for a wide range of classical machine learning algorithms. And the compute node here is an accelerator design. The goal of this work is that the programmer doesn't have to go through the design and verification cycle of hardware design, but they can get the benefits of hardware acceleration. As I mentioned, Tabla is a full stack solution. We provide a programming language which allows the user or a programmer to express their machine learning model, which they want to accelerate using a high-level mathematical language. And automatically, the compiler converts it into two things. One, the accelerator design, which is tailored for the model that is expressed, and what executes at runtime, both the operation scheduling and the data mapping. The goal here is that we want to completely remove hardware level details for the programmer so that they can easily leverage hardware accelerators for both performant execution and energy efficient execution. Overall, if we think about a full stack solution, it's trying to strike a balance between generality and specialization. Creating a full stack for one model or one feature size would not be very useful. Instead, we want to capture the commonalities across a wide range of models and create a full stack which can cater to all of these models. Specialization, because it's a domain specialized computational stack, and the accelerator should be able to do energy efficient and high performant execution. In the past, CPUs have been extremely general purpose, and they have used instruction set architecture as the abstraction between hardware and software. However, we have to rethink these abstractions now because we want to exploit the properties of the domain, which is the data flow properties and the operation properties that we commonly see across these wide range of models. Before I dive into what these novel abstractions for our full stack solutions are, let me give a brief overview of the target application that we are trying to accelerate. The goal of these machine learning models is to extract insights from data. And most of you might already know this, so please bear with me. They have two phases, the learning or the training phase and the inference phase. During the training phase, we have some training data, and based on the machine learning algorithm, it could be a linear nonlinear equation, clustering algorithm, or a neural network, we generate the final trained model, which then on unseen information can be used to make predictions. The training phase is more compute intensive and has more operations. So that's the target phase for all the systems that I described today. But we have created solutions that cater specifically to the inference portion as well. Diving in a little bit deeper into supervised machine learning, learning is like solving an iterative optimization problem, where we have some training data consisting of independent variable X and dependent variable Y. We begin with an initial model. This could be a nonlinear equation, and the goal here is to find the parameters of the nonlinear equation which best represents the training data. We iteratively go through the training data to find the predicted output, compare it with the golden output to see what is the loss. The final trained model is obtained when this loss is minimized. There are various ways to minimize the loss function. However, we often use iterative optimization techniques such as gradient descent based methods or stochastic gradient descent, which is a specific example of gradient descent, where we go through certain part of the training data to update the model in every iteration. the equation here that we see is a stochastic gradient descent example where it specifies how in every iteration, each input and output pair updates the weights. And we say, as we learned in high school calculus, to minimize a loss function, to minimize any function, essentially, we go in the negative direction of the differential of that function. Overall, if we think about this particular equation, this has two parts. One is the loss function, which is specific to the model. And then there's also an optimizer which specifies how the weights are updated in every iteration. And this is something which is common across a wide range of machine learning models. And this is the iterative update rule and specifies the entire training process, because this mathematical operation has to be repeatedly performed on the training data till convergence is met. And this is so commonly seen across a wide range of machine learning models that defines the abstraction for our full stack solution. We say that any algorithm in which there's a loss function and we can specify an iterative update rule, we can automatically convert it into a hardware accelerator and its runtime schedule and operator mapping, which we prototype on an FPGA platform. So our backend was an FPGA, but we also can create backends for other platforms as well. So this figure here shows the full stack solution that we created, the Tabla's full stack solution, where the programmer specifies the algorithm using a domain specific language, and all they have to provide is an iterative update rule. Once they provide this, the remainder of the stack automatically converts it into a FPGA synthesizable RTL for a multi-threaded accelerator. Now, first, let's look into what this domain-specific language is and what are the properties that we embody in this language. It's a mathematical DSL. And the reason for that is twofold. One, the mathematics of the domain has the maximum possible parallelism which the accelerator can exploit. Also, the programmer who's specifying the model is closest to the mathematics of the domain. So to just give an instance and an example of this domain-specific language, we take the logistic regression model. The loss function gradient here is specific to logistic regression, and this optimizer here is stochastic gradient descent. I just showed the stochastic gradient descent optimizer, but we can have other iterative optimizers as well. To convert this mathematical formulation into the Tabla programming format, we just have to convert every part of this equation into its textual format. The programming also maintains some of the semantics of the machine learning training data. For instance, we have model input and output, which specify the independent and dependent variable. This is the training data. We don't update this in the training phase, so this can be stored in read-only memories in the accelerator. We have a model which gets updated in every iteration and remains stationary on the accelerator design. Now, just to convert this formulation into Tabla programming, we convert every part of the equation. It could be a group operation, a scalar operation, or an element-wise operation into its textual format. Now, once this is all the user has to provide to express what is the mathematics that they want to actually accelerate. And once they provide this iterative update rule, the model compiler automatically converts it into a data flow graph. Now, once we have this data flow graph, we essentially know what is the parallelism that is available, what is the order of the operations, and what operations are actually required to be performed in every iteration of this machine learning training process. Now, once all of this information is available, the design builder and the constructor automatically convert it into the hardware accelerator. But as we are allowing a full stack solution, that means the programmer can provide various machine learning models and various feature sizes. So how do we create a tailored accelerator design? How do we create an adaptable accelerator? In Tabla, we come up with templates or template-based architecture, where the hardware design is actually hand created. We created this and it embodies the properties of the domain that we want to exploit. But this template is expandable and can be shrunk in certain dimensions based on the data flow graph, what is the width and the depth of the data flow graph, which essentially represents the algorithm requirements, and what are the constraints on the FPGA. So this template architecture that I'm showing here, this is one type of the template architecture targeting classical machine learning. It's a hierarchical design consisting of processing engines, which perform every scalar mathematical operation. And these processing engines combine to form a processing unit. These processing units perform essentially larger operations such as dot products and matrix multiplications. Diving in a little bit into this accelerator, each processing engine which performs every scalar mathematical operation is essentially a three-stage pipeline, where we have a distributed memory, which every PE contains the data, the training data, and the model, the data it operates on, and the model that it updates. Even the capability of the logic unit is determined by the operations that were required in the data flow graph. Another property that this template exploits is that we can do data parallel training. If the resources on the FPGA allow, we can do multi-threaded acceleration where every thread is actually executing a copy of that data flow graph, but on different training data. Now that we have these certain data flows that we require to execute the machine learning algorithm, the connectivity and busing logic on this template design is also tailored towards the domain. We have a multi-tiered bus to combine the weight updates generated by each thread. We have bidirectional links between the processing engines to do low latency reduction trees and scatter gather operations. And we have a programmable memory interface to stream in the training data into the necessary processing engines. Overall, if we take a step back and think about it, this is another entry point for our full stack solution, where the hardware design experts can create different templates. It can be tailored towards classical machine learning. We created templates for robotics. We also created templates for deep learning algorithms as well. But one thing the template architectures facilitates is that it provides a hardware design that contains the properties of the domain, and the programmer, whenever they decide to accelerate, do not have to go through the design and verification process. That is decoupled from this, and the hardware designer can do this design and verification process independently for the model that they are, or the domain that they are trying to provide this template for. Overall, Tabla took a very algorithmic approach towards acceleration. The language, the compiler, and the hardware design are all caters to the mathematical properties and iterative update rule of machine learning models. And it aims to tackle various challenges that we discussed in the beginning about barriers to custom hardware, because it does not require expertise in hardware design. Instead, it provides a high-level programming interface. At the same time, it's able to provide high performance and energy efficient execution because the template architecture is specialized and it is general across a wide range of models. So we don't have to go through the design verification cycle again and again. Moreover, the Tabla accelerator is performing end-to-end training and does not do limited kernel level acceleration. We use Tabla to generate accelerators for a wide variety of classical machine learning algorithms like logistic regression, neural networks, regression analysis, recommender models, and support vector machines. And we observe that they provide high speed up compared to high-end CPU and high performance per watt compared to high-end GPU. The reason for that is that the compiler does the static scheduling of every operator and data mapping prior to execution. So the control flow is really simple and it can mitigate a lot of the von Neumann overheads. Also, the accelerator is adept at extracting fine-grained parallelism. And all of this is done by writing less than 50 lines of code in the Tabla domain-specific language. The entire full stack solution of Tabla is completely open source. It was the first work to make the hardware accelerator also, the RTL of the hardware accelerator also available.
So Divya, can you, I definitely love the Tableau work, but I love your thoughts on the actual need for DSL, given that there are some established, frameworks like TensorFlow and PyTorch. How much more is it bringing for you, and how much could you infer from existing ways of expressing models? Yeah.
Yeah, I think that's a great question. This work, when we started thinking about Tabla, there were no domain-specific languages that had the abstraction of loss function and optimizer. This was prior to TensorFlow and PyTorch, and I do think that the way the PyTorch and TensorFlow allow the user to have this high-level programming abstraction of loss function, optimizer, autodiff, that's actually very important for the productivity of the programmer. And with Tabla, that's what we saw, that those abstractions between programmer and the hardware are super critical to make sure that we allow the hardware designers to be able to use different heterogeneous compute platforms.
Yeah, that definitely makes sense. And what are your thoughts on this approach, given that, models are becoming a lot more complex, right? More dynamic behavior, control flow, they're becoming more and more like general purpose programs. So do you think, a template-based approach would still work with you, or eventually going to go something that looks very close to a microprocessor today to be general enough, right? So
no, actually, that's a great question. I think the goal of template is to be able to cater to the compute intensity of the applications. Then recent models like language models that we are seeing, they can definitely gain from specialized hardware designs that we create. But yes, I don't think that one template would work for all. I showed one template architecture, but if we have abstractions between hardware and software, for instance, we have a capability for the hardware design to specify what is its schema, what is the capabilities, what are the operations that it performs. Then the hardware designers can continue innovating in the space of architectural exploration and create hardware designs which could be tailored for classical machine learning, doing GMM operations, doing activation functions, or even doing, for instance, sparse execution. But at the same time, it would be opaque to the programmer, and they should be able to leverage these hardware designs.
Yeah, great thought. Thank you. Any other questions, everyone? No? Okay. All right, keep going. Please, everyone, use the chat or signal for me, okay?
So when we think about Tabla, the goal there is to provide hardware designs that cater to the compute intensity and perform the execution of the machine learning training process. However, if we think about the larger data processing pipeline, it's important to account for data storage, retrieval, and pre-processing as well. So to tackle this challenge, we create the framework Dana, which integrates our full stack solution, which could be Tabla or DNN Weaver or Robox within relational database management systems. Dana brings together three very important aspects of database analytics. One is in-database analytics, where the ML algorithm is performed within the database management system, high-level programming paradigms such as Python and R. And as Luis was mentioning, we have these high-level programming abstractions which allow the user to easily express their machine learning models, and modern acceleration platforms that provides order of magnitude higher performance and energy efficient execution. Now, in this case, we integrate our accelerator directly within the database. All of the tasks which are data management are performed on the CPU by the database management system. First thing the database RDBMS does is it brings the data, the training data, into the buffer pool. And the accelerator directly integrates with this training table in the buffer pool and provides a specialized engine called the Access Engine, which imports the data pages and extracts any necessary features required to execute the machine learning algorithm. The accelerator Access Engine consists of a component called Striders. It operates on multiple pages at a time because we have to do pointer chasing between the database page to determine where the tuple is. So all of these striders in parallel extract and process the page header and process the database tuple to send the training data to the machine learning accelerator. Now, once we have the data that it needs to be trained on, The algorithm specification is provided using a high-level programming interface that we embed in Python, where the user has to provide three things: the update rule, which I was mentioning in Tabla, the merge function, which specifies how multiple of these update rules, which execute on the multi-threaded accelerator, are combined, and then finally, what is the convergence criteria? Overall, if we think about this acceleration, the accelerator understands how the data is stored, and it can pipeline the data retrieval and data pre-processing with the actual machine learning training process. We use Dana to generate accelerators for a wide variety of classical machine learning algorithms, and saw that it provides high speed up when compared to an in-database analytics library. And the reason for that is a lot of this speed up is obtained due to striders, because they completely bypass the CPU in the data retrieval and pre-processing phase. Overall, if we think about Dana and Tabla, the goal is to cater to the machine learning training and the compute intensity of the applications. However, as we go to scale and the scale of the models is growing, the memory and IO are also becoming very critical. So to tackle this particular challenge and to look in the context of memory and communication, we create our framework FAE, which dives into high-level statistical properties of the training data and the context of the application to determine what is the best way to use the memory hierarchy, the memory that we have on the CPU and distributed GPU devices. All of us typically encounter many recommendation models on a day-to-day basis. Netflix uses it for movie recommendation, Amazon for item recommendation, YouTube and Facebook to give personalized experience to users based on their past behavior. These recommendation models store a lot of data pertinent to what are the features of the user, what are the features of the item. And this data is essentially stored in embedding tables. One of the largest models today by Baidu has terabytes of embedding data. So this portion of the recommender models is very memory intensive. But they also have a compute intensive portion, which actually provides the recommendation at runtime. And with the advancements in deep learning and the attention layers, this portion of recommender models is also becoming more and more compute intensive. Often there's a disparity between different parts of the recommender models, and the embedding tables are stored and executed on the CPU, whereas the neural network portion are executed in a distributed GPU setting. This hybrid execution mode actually has inefficiencies. We saw for certain very commonly used recommender models, the CPU to GPU communication can take up to 22% of the total training time, and all of the computation for the embeddings is also executed on the CPUs. But there's one assumption that we are making here, that how much ever this embedding table size is, all of the embeddings are equally important and they have to be stored in the same place. Instead, in real world, we observe a very high popularity skew in the training data. All of us must have observed that in any point of time, one movie, one item, one product will be way more popular than the other. So how does this high popularity skew manifest itself into access skew during runtime? What we observe is in this graph here, on the x-axis, we see the workloads. On the y-axis, we see the embedding table size. A very small portion of embedding tables caters to more than 75% of the inputs. To put this into context, one of the largest model here today, Criteo Terabyte, the size of the embeddings, which are very highly accessed, is just 400 megabytes. And that can easily be stored on any GPU close to the neural networks. And that's less than 1% compared to the total embedding size, but they cater to 82% of the input data. So how can we use this information for end-to-end efficient execution? The architect in me says that if there is some data which is accessed significantly more than the other, we should store it closer to the compute which is on the GPUs. But just by storing these hot embeddings onto the GPU, we cannot directly achieve high performance execution. Instead, we face various challenges. The first question that we have to ask is, how do we even determine which are the hot embeddings? So first, how do we convert popularity into a quantifiable metric? Popularity is a pattern seen in the training inputs. How do we convert it into a metric for the embedding hotness? We have an access threshold where any embedding entry which is accessed more than the threshold is a hot stored on the GPU. Any entry which is accessed less than the threshold, which is actually stored back on the CPU. And this access threshold is determined based on the amount of GPU memory that we have for the embedding tables. A very high threshold would mean that very few entries are categorized as hot, whereas a very low threshold would mean a lot of them become hot and cannot be stored on the GPU. Now, once we have this threshold, how do we determine the hot embeddings? In the most rudimentary fashion, we'll have to go through all of the training data, keep a count of the embeddings, how many times they are accessed, and then compare it to the threshold. But this is a huge overhead because we have to process the entire training data. Instead, what we observe is that just using 5% of the data, sampling the data, also follows the same access pattern as the original data. The reason for that is that certain embeddings are accessed 10,000 times more than the cold embeddings. So the same access pattern is very easily also observed in a small sample. Now, once we know which are the hot embeddings through the sample of data, we store them on the GPUs. All the inputs in a mini batch, because we do training on a mini batch, they have to be stored locally on the GPU. They have to only access the embedding entries which are on the GPU. If any input accesses embedding non-popular or cold embeddings, then that would determine the iteration time. And this becomes even more challenging because we want to use a larger mini batch size. We observe that if we do not do any pre-processing and the mini batch size is increased, the probability of finding a mini batch that only accesses embeddings on the GPU, assuming 99% of inputs are popular, quickly goes down to 0. So we have to do some pre-processing and segregate inputs into popular and non-popular categories, where the popular only accesses embeddings on the GPU and the non-popular accesses embeddings all over the place. And this means we have to create these new mini batches. But the next question that comes to mind is that if we are doing some segregation, are we reducing the randomness of the machine learning training process, and can that have an impact on accuracy? To tackle this final challenge, we create a runtime scheduler, which takes feedback from the PyTorch module and makes sure that the loss is actually converging. And if it's not, it sees any disparity, then it shuffles schedules between popular and non-popular mini batches so that the non-popular mini batch can update the embeddings which are significantly diverse. By tackling these challenges, we create an end-to-end acceleration platform for general recommendation models called FAE, which on the training data samples and profiles it, determines the access threshold, it classifies the embeddings based on this threshold, and at runtime shuffles schedules to make sure that the loss is actually converged. Overall, the fundamental property that FAE exploits is that there is always going to be high popularity skew in the training data, because that is as high level as user behavior, where always there'll be certain items or certain movies, for instance, which will be way more popular than the others. We integrated this framework with PyTorch in general, so anybody training any recommender model can use FAE. We compared FAE with deep learning and time series based recommender models, by Facebook, which we integrated with the deep learning framework XDL. And we see that the runtime shuffle scheduler allows FAE to meet the baseline text accuracy across all the models and datasets. And it does so by taking 60% less time than an optimized deep learning framework baseline code and 80% less than the open source code. But another very important aspect of FAY is that it reduces the data transfer between the main memory and the GPU HBM by about 50%. And this is even more important because data movement is becoming the energy bottleneck for these deep learning models. It does incur an overhead of 13%. The reason for that is the calibration of hotness of embeddings and classifying them. But most of that can be completely moved to runtime during the training process.
Hey, Divya, there's a question
Yes.
here in the chat for you. So Aditya, do you want to just pick up and ask a question?
This is very interesting. I was just curious. So your technique basically proposes moving hot data to the GPU and keeping it in GPU memory. Mm-hmm. So like there's a feature called, which you're probably aware of, called like NVIDIA UVM, which does the same thing. The data is allocated and kept on either the CPU or GPU memory based on like how frequently it's accessed by which device. So I was just curious, like what do you like add over that, and have you like compared to a UVM based technique, and like how do you compare against that technique basically? Thanks.
So here we are taking a very deliberate approach for recommender models where we know that these embedding entries can actually be cached onto the GPU, for instance. The approach that you're mentioning is more general purpose and would have overheads of dynamic caching, which we actually completely eliminate. We do the calibration of hotness of the embeddings once during the every training execution run, because we know that that calibration would not change. And we can recalibrate it once again a training happens, but we do not incur any of those dynamic caching overheads. We did compare against the recommender deep learning framework by NVIDIA, in which it does some form of caching on the GPU accelerator, and we still provided higher performance. And it's actually the subsequent work after the FAY work in that we do all of this calibration dynamically. And the biggest benefit that we get over the purely GPU work is that we do not need as many GPUs to do the same training acceleration, because here we are splitting the data, the recommender model data, across both CPU and the GPU devices, which would not be catered by the solution that you were mentioning.
Can you just quickly explain what you mean by dynamic caching? I'm not familiar with what that means.
So it would mean that you would have to constantly figure out which is the more high access data and make sure that it is during runtime brought into local HBM of GPU. Instead, knowing the application context here, which is recommender models, we know that certain training data is way more popular than the others. So we can also do some of the determination and calibration of hotness even offline. So we don't have to incur and keep track at runtime which is the hot embeddings, and make sure at runtime, the approach that you're mentioning would have to at runtime keep track of which embeddings are hot, which are not. Here we know that the training data has certain training skew, and we can use that information to determine exactly which embedding entries are actually hot by just sampling, let's say, the first 5% of the data.
That makes a lot of sense. Thank you so much.
Zooming back out, as I was mentioning, we need to create solutions for the scale of problems that we are seeing. We need to create solutions across the system stack for the compute intensity, making sure we are looking at the entire system, memory and IO, and then even accounting for the statistical properties and approximate nature of the models that we are training. Like any researcher and scientist, I strive to have impact both in academia and industry. Before the Tabla work, we used to think of hardware acceleration, where we just kind of accelerate a kernel and look at it in a very ad hoc manner to the general purpose platforms. Instead, Tabla and its follow-on work that we did paved the way for domain specialized computational stacks, and we worked closely with Xilinx and Samsung to integrate them within their hardware tool chains. Moving on. For the past 3 years, I've been working in creating the next generation massive scale AI supercomputers at Microsoft. I specifically work in creating the synchronization algorithms when training and inference is done across thousands of accelerators. As we move and look into the future, the demands of AI are continuously evolving. As I was mentioning in the beginning, GPT-3 has 175 billion parameters, and it is anticipated that doing one training run of such a large model would take weeks on thousands of GPUs. So at the same time that the scale of the models is growing, their compute intensity is also growing significantly. So we need to create principled and deliberate solutions which dive into both the algorithmic properties of the model and the statistical properties of the training data so that we can use the memory hierarchy efficiently and create architectures which are tailored to these properties. As we all know, AI is becoming the driver for the next generation data centers and edge platforms. I want to look at creating architecture and system level solutions for large scale models, both training and inference. How do we think about the wider data processing pipeline in context of database systems such as unstructured and geographical data, which is becoming very common? So kind of accounting for the wider end-to-end data processing pipeline. Also, as the cloud effort scales, the impact of computing on environment is also steadily growing. So how do we keep sustainability as a first order consideration as we create these next generation data centers? Diving in a little bit into architectures and systems for at-scale AI and ML, how do we design and explore the architectural space to truly leverage the heterogeneity, the emerging heterogeneity in the data centers, which is GPUs, ASICs, FPGAs, and the execution mode is becoming very asynchronous and disaggregated. So we have to keep in account the properties of the platforms and the properties of the application domain. So for instance, a lot of these large scale models are trained in pipeline parallel, data parallel, horizontal parallel modes. Would it help to explore an architectural space where each pipeline stage is having a different architecture and running a different part of the model? So kind of exploring the architectural space so that we can answer the fundamental question that are the model architectures being created because we have fixed accelerators like GPUs to only cater to them. Another direction that I want to look at, how do we devise systems that account for large-scale distributed executions, especially in a federated learning scenario where there is storage, compute, and communication variability. We need to incorporate the statistical nature of machine learning models to understand if we can create solutions that cater to stagglers, for instance. Also, finally, how do we integrate domain specialized solutions with data sourcing and retrieval in addition to the compute part, integrating specifically these solutions with unstructured and geographical databases, which are becoming very common in disaster management scenarios. And finally, how do we examine every architectural and system level solution through the lens of sustainability? Preliminary studies shows that creating silicon, using it, and decommissioning it, all of this has a carbon footprint. So how do we explore the architectural space in a wider fashion so that we can create these accelerators that can be used for longer? At the use time, how do we provide a knob to the user where we can make the execution cheaper in terms of carbon footprint, based on what the application is, the context of the application, the time of the day it is deployed, and the geographical location. And finally, keeping in mind the statistical properties of the data and the caching properties of the model, how can we increase the end-to-end system utilization? Overall, I believe that the problems that we are seeing require us to collaborate across the stack: architectures, circuits, programming languages, compilers, databases, machine learning theory, to create co-optimized solutions which account for the context of the application and can provide end-to-end efficient execution. Thank you very much. And now I'm happy to take any more questions.
All right, thank you. Thank you, Divya. Questions?
I have a question.
Yeah, Magda, go ahead.
So one question. So yeah, very interesting. This is super cool work. So thank you for the great talk. I have a question about the second piece of work, the Dana system. So if I understand correctly, Dana will expose kind of its interface directly to end users who then kind of write their ML and then write their SQL But it might be also an interesting kind of design choice to create an accelerator and expose an API to query execution engines. And I'm just wondering if that would end up being strictly similar, or if there are kind of other opportunities for optimization, since many modern database systems will also try to kind of expose both ML and data management capabilities.
No, that's actually a great question. In the Dana work, our goal was not to accelerate the data management and even running simple analytics queries. We can definitely do that, but there, when the accelerated execution of queries happens on databases, even on GPUs, the biggest property that is exploited is that there is a HBM memory which has significantly high bandwidth than an external DRAM. And then the GPU can perform parallel executions on the accelerator to perform that query. In this particular case, our goal was a little different. We wanted to accelerate the machine learning algorithm, which is advanced analytics, and we wanted to pipeline data retrieval and pre-processing, any of that is required, and completely eliminate CPU from that execution process. So I kind of see some of the similarities in both these aspects that you're mentioning. One is accelerating the database queries versus doing the more advanced machine learning algorithms. But here, the benefit that we are getting is from catering to the compute intensity of the ML algorithm and not the data intensity that we get from the HBM.
Oh, great. Thank you. So actually, if I may clarify, so my question was a little bit different. So if I think of systems, maybe Google BigQuery would be one example. Those systems actually expose an interface that combines both the machine learning and the analytics, so that the users already have that kind of interface. So we could also have the Dana accelerator kind of embedded within such a system and still running the ML. But then kind of, since it's actually not exposed to the user, I was just wondering if there might be some additional opportunities for optimizing. But I think it might be actually, it will probably be equivalent though.
We do provide the SQL query. I completely understand. So yes, we do want to expose this to the user so that the user can say dana.linear_r, which is actually executing linear regression on every tuple of the database. But the user, all they have to do is express the linear R function in Python, and they have to express the SQL query.
Yeah, thank you.
Great, thank you. Time for a couple more questions.
Yeah, actually, I had a question.
Oh, hey, Kevin.
So David, the trying to keep the hot items on the GPU memory, you mentioned that that's going to, change the training, because now you're not doing sampling with a replacement any longer, or even a shuffle, and you could potentially bias the solutions. Have you done any checking or benchmarking of whether that biasing yourselves towards those hot items actually hurts performance in inference?
No, actually, that's a great question. We did check the validation and text accuracy, and all of that was same as the baseline. The one thing that we noticed was that it's not training more on the hot mini batches. Instead, it is very important to intermittently train on training data which is not popular, so that we can capture the tail end in the model representation. That is what contributes significantly to the diversity of the model. We did see accuracy loss when we did not, for instance, the rate of popular and non-popular mini batches that we had was 3:1. And if we had anything more than that, we saw that we saw accuracy loss in the end-to-end training process.
Oh, interesting. So, I mean, does that mean then you cannot hope to get a speed up of more than a 3x gain if you have to every third mini batch you have to go to a not hot sample off the GPU?
The one thing that we do to mitigate and get higher benefits is that we provide, and this was the subsequent work. So you're absolutely right for the Fei work, but for the subsequent work, we had a hardware accelerator on the network where it gathered the parameters, on the main memory while the hot mini batches were actually executing. So kind of pipelining the parameter gathering with the actual execution. And in those cases, we actually saw higher speedups.
Okay, all right. So feel free to follow up over email, and you reach out to me as well, and then I'll definitely follow up with her after the visit. So thank you very much again, Divya. It was a fantastic talk. Let's thank Divya one more time again.
Thank you so much, everyone.
We'll see you soon.